And here we have Jirka on simple essence of overloading.
Hi everybody. Today I'd like to talk to you about our joint work with my advisor, Brachthäuser, about distilling this simple essence of overloading. First off, well, what is overloading? Let's look at an example. This function takes x, an argument, and calls show on x plus 1. But, well, what is the x, right? Is it addition of integers? Is it addition of strings? I hope not. Is it addition of two vectors of size 2 of integers, perhaps? So the goal of overloading is to resolve unqualified ambiguous names into qualified names based on the type context, at least for this talk. So the most commonly used implementation strategy and part of the theory is just using backtracking. This is the same example, it's just ANF'd for, well, we'll figure that out later. I'll explicitly write those two overloaded names here with the two overloads. And let's start the inference process. So we start at y is add of x plus 1. And we say, oh yeah, it's addition of integers, because that's the first overload we have. We deduce that x and y have type int. And then we move on to the second line of the program. We take the first overload for show, which is showing of strings. And we get that y is a string. Wait, what? I thought, what? OK. Now y is supposed to be an integer and a string. So that's a contradiction. And this is exactly where we need to backtrack. So we go back. This is fine. Let's continue. Take a different overload for show, this time one taking an integer, returning a string. And, well, this works out. So we're done, right? Well, except we're not done yet. Let's look at a table of all of the solutions. We've only seen the first row, so we've seen addition of integers, but we haven't actually tried everything. And we want our overloads to be unambiguous. Therefore, there has to be exactly one green tick. So we do need to check all of the combinations. Now, I'll claim that backtracking is somewhat anti-modular. Here's a type checker pipeline. We gather the constraints, solve them, and then continue. And when we add overload resolution via backtracking, something weird happens, right? The constraint solver can fail. Bad overload, it's so over. Going back to the constraint gathering, which then can find a new overload claiming that it's so back. Even worse, we as language implementers need to implement our type checker state so that it's snapshotable and restorable. And there's been at least one paper doing the exact thing I'm talking about. And for the programmer, this is very hard to reason about, not to mention the error messages. So to call back to a previous talk, I reject the whole premise of this. What I want is to have modular overloading, to have this beautiful blue box that takes the result of constraint solving, does some magic, and resolves everything without me needing to change constraint gathering or constraint solving too much. So let's try to analyze the program again. This time, I'll ascribe type variables to x and y. And we notice that the argument x flows to the first argument of add. Now, let's do a little bit of wishful thinking. If addition is the addition of integers, then alpha flows to int, right? If we know the solution, then we know the flow. But if addition is addition of strings, we have a flow of alpha to string. And by the way, if you're scared of the inequality constraint, just imagine an equality. It's fine. We can also draw this. So there's a conditional flow from alpha to integer if we chose the addition of integers, and from alpha to string if we chose the addition of strings. OK, let's continue with the constraint gathering. I'll build up the graph so that we can see it. I'm simplifying flows through functions to make the diagram slightly more digestible. And again, there's a flow from alpha to int if we choose add int, and a flow from alpha to string if we choose add string. Note that the constraints we get are variational. The constraint only needs to hold if the condition above it is satisfied. Now, we can continue with the flow from the second argument, the literal one. If we choose addition of integers, then there's a flow from integers to integers. If we choose addition of strings, we get a flow from integer to string. And if you find this particular flow weird, well done. But let us proceed for now. OK. Again, if we choose, here we flow into gamma, into y. And if it's addition of integers, then it's a flow from integer. If it's addition of strings, then it's a flow from string. Now, finally, let's look at the input of show. So if show is showing of integers, we have this flow from gamma to int. And if it's showing of strings, well, it's from gamma to string. Now, I'm sure you believe me that the diagram is quite beautiful, but it doesn't actually help us solve overloads yet, right? Let's get back to the strange inflows to string constraint where add string is chosen. Now, using a many worlds interpretation, discovering such an invalid constraint tells us that the worlds annotated on the constraint are invalid. Therefore, we know that addition of string is a bad choice. Unless, well, int is a subtype of string, but please don't make systems like that. There's also a bad transitive flow from integer to string via gamma. And notice that this disqualifies all of the world where addition of integer was chosen, and at the same time, showing of strings was chosen. Similarly, there's one more transitive invalid flow from strings to integers in worlds where we choose addition of strings, and at the same time, showing of integers. Now, instead of having this weird side table on the right, let's incorporate this into the program itself. We have a core calculus, originally from variational types, which were used to model software product lines. And for each overload, we have a fresh dimension, though in general, they don't need to be fresh. And each has alternatives. From this, we gather the constraints to build a variational constraint graph. And it doesn't need to be a graph, just a list of edges is perfectly fine. And we get variational error constraints. So when your constraint solver fails, and it failed in some specific world, we see which descriptions of worlds are invalid. Now that we have the invalid world combinations, we can try to characterize all of the valid worlds. Now, valid worlds are all the possible worlds, so exactly one assignment per dimension. And at the same time, there can't be any invalid world. So not the first description, not the second description, not the third description at the same time. And now, as a reminder, we want to find an unambiguous valid world. And as a consequence of having this beautiful modular description, we can take a solver, like a BDD solver, for example, but I'm sure you all can find much better solvers than I could. And we plug this equation in and get very quickly out the number of assignments and the single valid one. Now, you might be asking, is this even practical, or is this just for your warm, fuzzy feelings? Well, it's straightforward to implement this. We did it in Rust. We compared performance to Swift, where Swift uses a Hindley-Milner-style type system. It uses a constraint-based system, and it has overloading, and it's a production language by a big company. And comparing to Swift, we can see that we're at least practical, though we found some fun examples of encoding return type overloading, where Swift times out after 9 minutes, telling the user to please split their expression. It scales quite well on artificial benchmarks, at least. This takes an argument and adds it together n times with m different overloads for addition. And it scales quadratically in each dimension. And finally, if you're not convinced by this, we also have a web playground. So you can go ahead, type up exactly the example I've shown, change it, and see how you manage to break the system. Now, in the paper, there are many more examples. There's a description of how to apply this for both a Hindley-Milner-style type system and algebraic subtyping. We have a formal description of the system and its meta theory. Choices can have arbitrary expressions inside, which might be fun for something like UFCS. There's slightly more descriptions on many worlds interpretation with a modal context, and we tell you how to encode this into a binary decision diagram. So the simple essence of overloading is that it's a flow-based, practical, modular way to infer type-based overloads. Thank you for your attention.
We have plenty of time for questions.
Hello, thank you for the amazing talk. Do you have any plans to scale this to an ML system with local-let generalization?
Thank you for the question. Currently, we were not planning on supporting local-let generalization, as is. That's also, there are many authors of papers who do claim that if you have a function which takes, let's say, a person and return person.age, this should be generalized into some great type which tells you for everything alpha that has an age, this returns a beta, where the beta is the age. And for now, at least, for the very simple essence, we've decided to not do this.
Hey, thanks for the great talk. Have you compared this to Haskell type system and its type classes? Because to me, I don't see the difference between these two. And they've solved it without using an external modular solver, just by you doing inference.
Yes. There are two cases, I think, in which you might want to use overloading. One is you already have overloading, like most production languages, unfortunately, and want to get out of the mess you got yourselves into, 20 years ago. Or in the case of Swift, like 8. That's one use case. The other is we can guarantee, this happens during compilation, so we can guarantee there are no dictionaries being ever passed around, and we don't need a single principal type. So for example, Rust plans to add variadic generics in order to support like addition of 2 things, 3 things, 4 things, 5 things. And here we can do it in a sort of unprincipled, very local way.
Okay, thanks.
I think my question was the same as his, which is, right, type classes are very popular as a way of dealing with overloading. And main languages have them, like Rust has them in the form of traits. So can you play nicely with type classes and get both?
Yes, I certainly hope so. I haven't tested it out, but there's nothing that would indicate that it's not possible. And Swift does this. Swift has both overloading and type classes.
Right. Except they don't call them type classes, they call them protocols.
Yes, that's true.
Okay, thanks.
Thank you.
Do you have a general complexity bound for any programs? So you have a specific example, but in general, static overloading is NP hard by reduction to freeset.
Yes.
So.
Yeah, exactly. One of the benchmarks is even I need to go through all of the beautiful build-ups. One of the benchmarks is called freeset, and it's exactly Eric Lippert's encoding from 2008 when they added delegates to C#. And yes, it's NP complete, and this is partially because of return type overloading. And there's just not much you can do about that.
Okay.
Thank you for, if I was being mean, I'd say thank you for an interesting ICFP talk. This question is dubious in more ways than one, which is that at OOPSLA', there was a paper which pointed out, I think it was by Todd Milstein, that for multi-methods, which is to say almost dynamic multiple argument overloading, you can't be modular and symmetric. And what was the other clause? Modular and symmetric. Certainly you can't. And there was something else. Oh, I can't remember. Basically, it says there's a result there that this is something you can't do, but you seem to be doing it or something very close, because you're claiming to be modular and presumably symmetric. And
I would be very interested in talking later about the paper in question, because I don't exactly see the problem you're describing, but I would love to know.
I guess it is that possibly what you're using by modular, which means no backtracking in the inference algorithm, if I could talk about what you said, whereas their definition of modular means you can't cause overloading resolution failures by adding other modules.
Yeah. Okay, thank you. We can talk later. I'm very interested in the paper.
Okay, let's thank Jirka again.